Hey you guys, my name is Isaac. I'm here to introduce the problem we're doing today. Today we're going to see and compare the kind of difference of the forces needed to perform a push-up and also push-up weight on doing 1 rep on the bench press of your own body weight. As we see here, right here I'm doing a push-up right here, and you kind of see kind of the forces here at work and torques at work. So you can see right here as it's set up, you can see that I plant my feet here to make the axis of rotation right there down by my feet. You really can't see it, but your weight kind of acts at center of mass going down, and you can also see the normal force interacting between the force of me pushing up and the force coming back, allowing me to push up in this motion. And in a little bit, we're going to be transitioning over to the bench press, and we're going to see similarly here. You can see as the weight comes up, you kind of want to set up here so the bar comes down and comes up at an angle. So, and kind of the force that counteracts that, the X component of that push will be the friction of in this case my back on that bench press. And also apart from the whole axis of rotation where this barbell is moving up and down, there's also my body weight and the normal force of the bench pushing back up on my body. And as you see here, just a few reps of just pushing up the weight here, just kind of show how the motion's going, where you could probably see some of the forces acting on here. Kind of similarly as the force pushing up, and also it's kind of the whole movement in itself, just to show you guys an idea of the force itself in action and the torque itself as well. And in a little bit, I'll be passing it over here to Jason, and Hunter will be doing the calculations for these specific situations.
Hi, my name is Jason. I'm going to be describing the motion of a push-up and the forces and behind it. This is a free body diagram of from toe to head of a person's length, which is described in D2. And so some of the forces here are the normal force exerted by the floor on the feet, as well as normal force of the against the hands, and also the weight bearing down on the body. So on the center of the distance to center of mass, which is D1. And I'm gonna write all the forces in the x direction, which should come out to 0 because this object's not like moving up or down. I mean moving left or right. So let's do that. So the forces in the x direction are the force of friction versus the horizontal force of the second normal force. So that's what Fs minus m2x equal to 0. Fs is 2x. So that's for the x direction. For the y direction, the sum of the force in the y direction are your normal force on your toes and your normal force on your hands, and that's minus the weight. So that'll be what? Wait. And since again, like this, objects are going up and down, the forces are equal to 0, and they cancel out. Okay, so describing the torques in this system, if we take the axis of rotation to be right there at the base of the feet, the torques caused by the normal force on the feet and the force of friction is equal to 0 since it's at the axis of rotation. So your only true forces are coming from your normal force that's pushing up against your hands. And the force caused by the weight on your center of mass. So let's do that. sum of the torques are equal to 0, is equal to your normal to y, sine I d minus a d1 sine I d. And if you isolate your second normal force, you should get d2 sine theta. Now plugging in the given values we got from our subject. And you should get about 777 newtons pushing up against you, while the earth pushing up against you.
Hi, my name is Hunter, and I'm going to talk about the physics of the bench press. We're considering that we're bench pressing our own body weight here. So I've already drawn up a free body diagram. You have the weight of your body at the center of mass and the weight of your body being lifted by your arms a distance apart here. And then you have the force being applied upward by your hands onto the weight, which goes at an angle backwards towards your head, like inverted. And then there's also the normal force that is applied to you from the bench that you lie down on. And so we're just gonna do some equilibrium equations here and see if we can figure out what's going on. So the sum of all forces in the x direction equals 0, since the object isn't accelerating. You remain in an x direction static while lifting. And this is going to give you, if we declare the right to be positive, so we give you Fs, the static friction force, minus F cosine theta equals 0, or Fs equals F cosine theta. Now if we do the same thing with the forces in the y, those again equal 0, since we're not accelerating up or down. Now if we do those, we're going to get F sine theta, the y component of your force on the weight, plus Fn, the weight being applied to you by the bench, minus 2 times W, because there's 2 times your body weight being applied down. In the statics, it doesn't matter where they are applied, they have the same force. That equals 0. So we're going to solve this equation for Fn, and that'll be obvious why we did that later. Now considering the torques for this equation, if we put the axis of rotation at our head, again the sum of all torques will be 0 because we're moving this weight upwards at a constant speed, so there's no angular acceleration. So the sum of all torques equals 0. Now if we look at all the torques, add them up, we get Fn d1 times sine 90 plus F sine theta times d2 minus W d1 minus W d2. There's no angle on these two because they're both sine 90, so for the sake of space I didn't write them out. Now we're going to come over here and take our Fn equation that we conveniently solved for earlier and plug it in. So that's going to give us 2W, oops, yeah, no, I was doing the right thing. 2W minus F sine theta times D1 plus F sine theta D2 equals W D1 plus D2. And then now it's just algebra. We're going to simplify 2W D1 minus F D1 sine theta plus F D2 sine theta equals W D1 plus D2. And we group like terms, factor out what can be F sine theta times D2 minus D1 equals, move this W over, factor out, W times D1 plus D2 minus 2D1. Factoring out, or not factoring out, simplifying even more, we get F sine theta D2 minus D1 equals W times D2 minus D1. I can probably see what's about to happen, but I'll write it out. In terms of F, our answer is W D2 minus D1 over sine theta D2 minus D1. These equal terms cancel out. Our final answer is W over sine theta. Solving that with our givens gives us just about 1,280 newtons. So as we can see from our data, the force of our bench press was 1,280 newtons, which translates to about 115% of your body weight, while the push-up only takes 770 newtons to lift your body weight, which is about 0.69 times your weight. So we've shown that when it comes to your own body weight, it's much more difficult to bench press it than it would be to push it up. Thank you.